Good afternoon, everyone. I'm Tianyu Lu. Today, I'm going to present our work, the first study on how advanced multimodal large reasoning models, or MLRMs, can infer sensitive geolocation from ordinary images, and why this constitutes a concrete privacy risk that currently defenses do not adequately address. Our work introduces a benchmark, a novel metric, and two analysis tools that together expose and quantify this problem. In 2019, a Japanese idol was stalked and outed after a man pinpointed her location by zooming into the reflection in her eye in a selfie and cross-checking the details with Google Street View. When she posted her photo, she likely never imagined that a casual snapshot could reveal her location. Recent MLRMs can integrate subtle visual clues with broad world knowledge to infer where a photo was taken, even when users do not share geotags. This new capability extends beyond captioning or recognition and reaches high-level inferences about geolocation. Under GDPR and CCPA, location and precise geolocation are personal and sensitive information, which raises regulatory risk when models reveal them from user imagery. The risk is amplified by everyday sharing of selfies and live photos. Innocent background details such as house numbers, signage, or architectural features can reveal home addresses or routines. With this context, we would like to define the space of harm. For formalized two boundaries, privacy space refers to the home or adjacent areas where people reasonably expect not to be entered, watched, or recorded, including interiors and nearby private zones. Personal imagery refer to photos where an identifiable individual is the primary subject. Building on these, we define a three-level visual privacy framework. Each level maps to specific GDPR and CCPA provisions, giving a principled basis for assessing leakage. We consider technically proficient but non-expert adversaries in a black box setting. They have only publicly available user images without geotags or auxiliary identifiers. They can access strong MERMs or MLLMs, both closed source and open source, and may use interactive capabilities supported by these systems. Even under these minimal assumptions, an attacker can combine subtle architectural, environmental, and textual clues to infer location accurately. To study the risk systematically, we built DocsBench, a dataset of 500 high-resolution images that simulate user-generated content across privacy-sensitive scenarios in California cities, with EXF retained for evaluation. To test generality, we add 50 level 3 samples from Google Street View across multiple states. Our scenes include personal and residential contexts that better reflect private settings than landmark-only images used by other concurrent works. We use the minimal prompt that asks, "Where is it?" with output constraints and the top K variant to elicit structured, checkable predictions. We report a verifiable response rate, which counts only responses that follow our predefined verifiable format. Then the average and median geodesic error distances is computed from decoded predictions. To unify whether the model answers and how accurate it is, we propose SCLARE, a novel information theoretic metric in bees that integrates refusal entropy with accuracy terms. We also report CCPA accuracy, defined by 1850-foot threshold of precise geolocation from the law. We evaluated 13 models, 7 MLRMs and 6 MLLMs, and compared them with non-expert humans on Amazon Mechanical Turk. For MLRMs, top 1 achieves 12% CCPA accuracy, and top 3 reaches 15%. These are non-trivial in real settings and underline the need for privacy-related safety alignment. We also find that advanced MARMs lower the barrier for non-expert. Mean glare exceed the non-expert baseline, and CCPA accuracy roughly doubles it. Notably, we discovered that prediction difficulty increases with annotation levels. These monotonic reductions indicate threat severity align with task difficulty and further prove the robustness of our three-level risk annotation. Our analysis of MLRM's reasoning process highlights clue-based reasoning, and we will further prove this by using COT in our prompt to guide MLRMs. COT improves the performance on both answered cases and unanswered cases on vanilla, demonstrating the importance of clue-based reasoning pattern. Using Clue Miner, we extract and group frequently used clues, regional and architectural styles, vegetation and lighting, sensitive elements such as license plate patterns, three-sign tags, regulatory tags, as well as waste management infrastructure. The distribution shows that models often rely on privacy-related clues and lack explicit mechanism to avoid them. We also propose GeoMiner, a two-stage collaborative framework. The detector model extracts critical visual clues, which are then passed to an analyzer model for location reasoning. This reflects a realistic non-expert workflow that supplies hints to a powerful model. The experiment result shows providing prior clues yields consistent gains in localization accuracy. Lastly, we assess several defenses. Llama Guard 4, a vision guardrail, consistently label all inputs as safe across benign and risky cases, failing to detect image-based location leakage. Manual blurring of location-relevant clues reduce VRR and glare on average, yet models still achieved 10.56% average CCPA accuracy, indicating residual risk. Gaussian noise helps only at high intensities that significantly reduces the information content of the information and shows instability across levels, which limits its practical utility. Overall, defenses face a fundamental trade-off between safety and utility, and none offer robust protection across settings. In conclusion, we present the first systematic study that frames, measures, and analyzes image-based location leakage in MLRMs. DocSpins provide real-world, privacy-relevant data. Glare unifies answering behavior and accuracy into a single risk-oriented measure. Luminer reveals what visual evidence model exploit, and GeoMiner shows how a simple two-model workflow can further amplify risk. Our results indicate that these systems can surpass non-expert at inferring sensitive geolocation from casual photos, and current defenses are totally insufficient. We hope this work grounds evaluation and informs the design of privacy-aligned model behaviors and policies. At last, please allow me to post a short advertisement here. Currently, I'm looking for PhD or research master positions. My research interests are artificial intelligence and computational biology. However, I'm also open to explore any emerging field. If you are interested in me or want to connect, please contact me via email or LinkedIn. You can find my CV on LinkedIn. That's all. Thank you.